the idea with the arc length is the same as the idea with the derivative dy dx. So we have, let's remind ourselves of some of the formulas that are involved in polar coordinates, and then our connection between polar coordinate graphs and XY calculus. So if we remember some of the ideas behind polar coordinates, just to remind you, we have the actual transformation where we have a couple of equations. We have x is equal to r cosine theta and x is equal to r sine theta. We also have on the side here r squared is equal to x squared plus y squared. And there's also the one with a tangent to find a relationship between x and y and theta, but I'm not going to worry too much about that. We'll call on that equation when we need it. But anyways, I think our approach was to look at to transition your polar coordinate graph into parametric form. And so if we change this into parametric form, we have this relationship x equals r cosine theta, but r is equal to f of theta. And y is r sine theta, where r is equal to f of theta. So if we take a look at that, then we're able to do the derivative dy dx based on this. And we saw that formula last time. But now we're also able to do the arc length. So let's do a quick recall. The arc length formula is the integral from some t values going from a to b. And we have the square root of x prime t squared plus y prime of t squared dt. I think that's the arc length formula. You remember? Yeah. Okay, so to change our polar coordinates into parametric equations is our first step, and then we put it into the arc length formula, which means we need to take derivatives of these things. So let's go ahead and do that. So we need x prime of t x prime of t. Now f of t, I guess this should be theta. F of theta is a function of theta, cosine is a function of theta, so we have to do a product rule. So I think we saw this also already when we were taking a look at the derivative. So it's a derivative of the first times the second plus the first times the derivative of the second. Derivative of cosine is negative sine. So that's x prime of t. I'm going to need to take that and square it. Not looking forward to that. So the derivative of y is essentially the same thing with sines and cosines. So the magic happens when you take the derivative, or when you square each of these things, you're going to have components like x squared plus y squared, or let's say that again. When you square these things, you'll have things like cosine squared theta plus sine squared theta that would group together. You'll have things that will cancel in the middle, and you'll end up with a simple formula. So this is the part that I will skip, and all the sines and cosines will disappear. Now, for the sake of practicing, you may want to do that. If you're tutoring people in pre-calculus and you're doing some trig with them, this would be a good exercise on dealing with trig identities. You don't have to do derivatives and stuff like that. You just say, hey, I got these two things. I need to square them, add them together, and then, oh, that looks like a cardioid or a limaçon. And then just tell them to square it and then add it, and then watch all the x squares plus y squareds cancel out. And this is when they ask you, why is this trig stuff so helpful? What's the use for it? You say when you're in Calc 3, this is what you got to do. All right, let's do an example of finding an arc length. I think I picked out this one, the loop, one loop of this rose petal thing. It was. I think the hard part might be, I don't know, that's, yeah, yeah. Well, so for starters, you have to know what the graph looks like, and this is where you get to use Desmos and plug it in, and then mess around with the thetas to see what the things might be. Or you could try to plot it by hand if you're adventurous like that. Just try to put in like 0 in for theta, and then pi over 2 in for theta, and maybe you might have to put pi over 4 or pi or whatever. So you can go through that thought process, and for that, maybe I'll do a little bit of that, and then I'll also graph it. For that, I would probably want to use a table just to find some values and then try to graph it. So when theta is equal to 0, that's an easy one. R is going to be equal to 1. So 0 is the positive x-axis, and you have a length of 1. Now the cosine is going to go. The cosine is going to start with 1 and go back down and go back up. Down at pi and back up at 2 pi. But this is 2 theta, which means is it going to be compressed or expanded? It's going to be compressed. So you're going to finish your period at pi. So I might be interested in finding out what happens instead of going to pi over 2. I might want to, because I have a feeling it's going to go there faster. I'm interested in what happens at pi over 2, but maybe I might be interested in what happens at pi over 4 because we're anticipating that it's going to get there sooner. So at pi over 4, I get cosine of pi over 2, and cosine of pi over 2 is 0. So it looks like between here and the angle of pi over 4, I'm already going to be at 0. So that looks like it's going to end up being one of the loops. And then when I get to pi over 4 to pi over 2, what happens at pi over 2? Cosine of pi over 2, 2 times pi over 2 is pi. What's cosine of pi? It's -1, right? Is it -1? So by the time I'm facing pi over 2, I'm looking up the y-axis. My r is -1. It's behind me. So imagine looking up. This is behind, so this thing must be drawn this way. So do we get some idea of how this is being drawn now? So it looks like it's going to be a 4-leaf clover, flower. And just by looking at that, it doesn't look like it's one loop. So I can probably trust that the loops are symmetric. So maybe I could just do one loop and multiply it by 2, or half a loop and multiply it by 2. Did I say that right? Yeah. So I might be interested in doing half a loop and multiply it by 2, or I can start by going negative pi over 4 to positive pi over 4. So either way, I think, would work fine. So those are our limits. So our options are to go from 0 to pi over 4, then multiply by 2, or go to minus pi over 4 to pi over 4, and then just take it like that. Now, I guess to me, it wouldn't matter because I'm just going to put it into Wolfram alpha or something. But, you know, if you're concerned about integrating and putting in the values, I'd probably go from 0 to pi over 4 and then double it. So let's set it up. Well, before we set it up, we need to find a derivative because it looks like we need the derivative and the original function, square each one, add them, and put them under square root. So I have my r. And I need my r prime. I'll just say r prime. So it's negative 2 sine 2 theta. And then I'll take each one and square it. So r squared is equal to, well, that's just cosine squared 2 theta. R prime squared is equal to minus 4 sine squared 2 theta. What? Oh, like that? And if I add them, I don't get the sine squared plus cosine squared because sine has a coefficient 4. So I guess I'm just going to have to put it into a computer. But anyways, you would write down that the length is the integral. What are we doing? 0 to pi over 4 minus pi over 4 to pi over 4. Cosine squared 2 theta plus 4 sine squared 2 theta d theta. So I did a little bit of the work there to try to figure out, see if it'll be nice and easy and things will cancel. It doesn't look like it, so let's go ahead and punch it in. Let's shrink anymore. Shrink, shrink. So this is a square root of cosine 2 theta squared plus 4 sine 2 theta squared. Oh, yeah. What? Negative 2? Does that look right so far? Okay, so that's inside of the cosine, and then my theta is going to go from minus pi over 4 to pi over 4. Negative. Yeah. All right, hopefully it works. E negative 3. What? All right. So there are some common functions that pop up in math that come up often enough that Wolfram, or I guess not just Wolfram, but a bunch of math people decide that it's worth naming a function after it. One example is you've probably seen this e to the t squared function as a function, one of those prime functions that we cannot integrate. So we can't integrate this, or at least we don't have an actual function that comes out of this. U substitution doesn't work, integration by parts doesn't work. But if you put it into Wolfram alpha, you'll actually get an answer. It's what? Integrate. What are we integrating? This is a little tangent, by the way. Wolfram is pretty forgiving about the notation that you use. So they call it an ERFI function. Wow. Have you guys seen that before? ERFI function? Oh, you have? Where? Oh, yeah. Yeah, it comes up in an ERFI function. And there's this weird 1/2 times the square root of pi business that comes up. So we're actually going to see that in this class. 1/2 square root of pi. Where does that come from? We'll see. I guess this is chapter 15. Well, we'll see it in chapter 15. Or statistics. You'll see it in statistics. Well, whatever. Maybe you won't. It depends on which statistics you take. If you take statistics here, then you probably won't see that because we don't do integrals in this stats class here. All right. So that's the last bit. They also talk about area under the curve between a graph and the x-axis and stuff like that. But that's kind of like forcing an issue that's really not that big of a deal. It's not a natural issue to talk about that in polar coordinates. So I think the area that we saw last time where you're doing sectors is more relevant to polar coordinate graphing than the area under the curve. But we have this power now to change polar coordinates into parametric form. And because we could do that, then we can address anything that they talk about in parametric form. So again, we're not too interested in doing that for polar coordinates because we have a more significantly relevant area problem in polar coordinates. So we'll just leave it at that. All right, we're going to move on to our next section, which is the conic sections. And for conic sections, we begin with something that you probably should have seen already. I mean, you might have seen all the conic sections already anyways. But we're for sure have studied parabolas sometime in our algebra careers, intermediate algebra, and in pre-calculus. But the thing that they probably didn't talk about when they talked about parabolas and algebra and pre-calculus are the idea of focus and directrix. And if you've seen this before, it's also a popular topic that is covered in I guess algebra 2, I don't know, you might have had that in high school, where they talk about the focus and the directrix of parabola. So the formal definition of a parabola, if you look it up in Wikipedia or wherever, is a set of all points that are equidistant from a fixed point, and they define these things about being equidistant from a fixed point to a line as a as a thing that's defined. But you know, I don't know if I guess that's an important aspect, important concept. But the idea is that you have a point and you have a line, and so anything that's equidistant from that point in that line. So if you have a point here that has the same distance from the point in the line, that is going to be part of the parabola. Now, if you pick another point out here, and the distance between the point and that line is not equidistant, then this is not part of the parabola. But if you find another point over here that's equidistant, and equidistant from a point means it's just a direct line from the point, and then I guess I was drawing it backwards. Maybe over here. So I guess I'll mark it with a, this is what they do in geometry, right? They put like one slash and then they have another length that's two slashes and that's same distance from, you know, same length. So if you collect all these points, you'll get is you'll end up getting a parabola. And the parabola opens up where the focus point is inside of the concavity and the line is outside of the concavity. And then if you go the straight distance from the point to the line, then you're going to pass through the vertex. Okay. Now the idea of parabola is that it could go sideways, it could go up, or go down, and just depends on what the equation is. So this set of paragraphs here talk about parabolas that are going up or down. So, and this is probably something that this is the equation that you might have seen before. So parabola or vertex at the point BC, and the focus is going to be the same x value. If it's going up and down, it's lined up along the x, the same x value. And then your vertex is just a little bit off. The y value is just a little bit off from the focus point. And then the directrix is going to be a horizontal axis or horizontal line. So y is equal to something. It's described by the equation a parentheses x plus b quantity squared plus c. And the parabola opens up or down depending on what a is equal to. So if we take a look at our simplest parabola, the very, very, very first parabola that we learned, we could try to figure out, we know some information about this parabola, we could try to figure out where the vertex is and the directrix and all that stuff. I want you guys to take a couple of minutes and try to figure out, well, let me graph it first, because this is easy to graph. So let's try to figure out where the vertex is. I'll give you a hint. The vertex is 0, 0. Focus and directrix. So take a minute or two, figure that out. Okay. If you figure it out, great. If not, let's see. If we write this as a x minus b squared plus c, we can identify a, b, and c. Looks like b and c are going to be 0 and 0. That's how we got our vertex. A is going to be 1 positive, so we can clearly see it's opening upward. And and so now we can find the focus. The focus is B, 0, comma, C, that's 0, plus 1 over 4 times A, which is 1. So it's should be 0, same x value, right? It's lined up along the vertex. And we're just down, or we're up a little bit by a quarter. So that's your focus point. Your directrix is almost the same. It's going to be y is equal to, and then it's going to be c, which is 0, and then negative 1 over 4a. So that's going to be negative 1/4. So now you're down here at negative 1/4. So that's it. Now you know everything about y equals x squared. Any questions? Okay. So we could have these parabolas opening upward. We could also have parabolas opening sideways. Sideways. Is this it? Yeah. So I don't know why they call it a theorem, but so this time you have x equals a times parentheses y minus b quantity squared plus c. So your parabola in this case is going to be opening sideways. If a is positive, it's going to open to the right. If a is negative, it's opening to the left. But you have a similar setup as the other thing. So let's make up a quadratic equation relationship between x and y, and let's see if we can figure out the vertex. Just by looking at the form of your parabola, you probably call it vertex form or something like that if you've seen it before. What do you think? What kind of algebra do you think you need to get it into that form? Completing the square. Remember how to complete the square? Okay. So let's do an example. Should I just make one up? Let's make up a hard one. Sure, what the heck? It's just algebra. let's see. Let's go y minus 3x squared plus 4x equals 10. Nah, yeah, well, 10 feels like it's too big. Let's go 5. 5 is probably too big too, but all right. Let's see if we can write this in the form that we want. I think the form that we want had either the x or y by itself. The variable that's not squared is by itself. And so if we bring everything to the other side, then we might be in good shape for completing the square. And there's probably a lot of ways to complete the square. So I'll do it my way, and then you could decide whether that's going to be how you want to do it. So the completing of the square will happen here on the right-hand side. And before I begin to complete the square, I notice that there's a coefficient in front of the x squared. So I want to factor that out. So I need to factor that out. Now, I'm only going to factor that out of the first two terms because I don't want to mess with a 5. And you know, when you factor out a term that doesn't have that exact factor, it's like dividing it out. So you get that. I'm going to leave a blank space over here because I need to figure out something to add in the parentheses and at the same time subtract outside of the parentheses so that I will have a perfect square. So what do I add? So in here I think about the b term, which does not include the x, by the way. I've seen this in pre-calculus classes. You guys are beyond this, right? They put x here, and then that gets really confusing. So just 4/3, the coefficient. And what do? You like take half of it, and then you square it. So 4/3, take half of that or multiply by a half, and then you square it. So I think the 4 and the 2 would cancel. So that's 2/3. Is that right? And then you square it, it becomes 4/9. So you add 4/9, and so you would subtract 4/9. Well, you don't exactly subtract 4/9 because you're subtracting 4/9. You're adding not just 4/9, but you're adding 3 times 4/9. So you have to subtract by 3 times 4/9 as well. Okay. I think that's good. And so the completing the square business just means that you get to write this as a perfect square. Same sign as the middle term. And the last term is always positive because you're squaring that. And you're taking the square root of that last term. So square root of 4/9 is 2/3. It's basically that number in the middle of the process right before you square it, which is the square root of 4/9. So that's your perfect square. And then you just do the subtraction as if this is easy. It's fractions. So that's 12, 9, that's 45. 45 minus 12 is 33. 4/3. So 4/3. So 15 minus 4, 11/3. Okay, there you go. So then now you can identify your vertex. Why is it not writing? Uh-oh, my pen's not working anymore. Heck. So the vertex is 2/3, comma 11/3, and the focus is going to be, this is up along the y, opens up and down, so it's going to be the same x value, 2/3, and then you have 11/3. It's opening upward, so it's a plus 11/3 plus 1/4 times a, more math, 5/12, 45/12. So it's 2/3, comma 45/12. Does that reduce? No. Oh, that's the x? Oh, that's if you're opening sideways with your x there. If you're opening up and down with your y by itself, then it's the y. So again, the way to remember that is that if you have y and then you have x that's being squared, then this parabola is going to be opening upward. So upward or downward. And since we know it's cube, or not cube, since we know that the a is positive, it's going to open upward. All right, so does this still look good? 15/4. And then the directrix. Since it's opening up or down, the directrix is going to be a horizontal line. Y is equal to, and y is going to be equal to the 11/3 minus 1/4 times 3. So yeah, y, horizontal. 44, 43, 43/12. Yeah. So let's check this. Let's plot some points first. So that's the vertex. Let's plot the focus. Let's plot the directrix. Oh, it's really close. Good thing we're not doing this by hand. So we got the vertex, the focus, and then let's finally draw the graph. Y is equal to, what is it? Y minus 3x squared 4x equals, was there a 5 in there? Yeah. There we go. Passing through, distances are the same. So, looks good. At this weird. All right. Any questions? That the directrix is the vertex? Oh, well, this wasn't labeled, but maybe we'll label it in green. And then the vertex is in red. So hopefully, if people aren't colorblind, they can distinguish by color. I mean, that's a serious thing. Guys, by the way, have more percentage chances of being colorblind than girls. And it's an issue, so we have to respect that. All right. So this is one conic section shape, the parabola, and there's a couple of others. There's actually like 5 or something like that. Technically, a point is part of the conic section, a line is part of the conic section, and then you have circles are parts of conic sections. And then beyond that, there's the parabola, and then there's 2 others, an ellipse and a hyperbola. So let's quickly introduce the ellipse before we go. And the idea behind these conic sections is that we want to be familiar with these graphs or get some idea of what these graphs look like. And by familiar, I mean equation and the graph. So that if you see something, say something? No. If you see something that looks like a parabola, you will identify it as a parabola. And if you see something that looks like an ellipse, you identify it as an ellipse. So an ellipse is a set of points in which the sum of the distances between 2 fixed points, called the foci, focus points, as the distances are constant. Why is it is? Set of all points for which the sum of all distances, the sum is constant. Is. That's correct. I was a grammar buff back in 7th grade. It's like math. It's just a bunch of rules and stuff that you have to follow. And memorize vocabulary terms like adverbs and infinitives. And anyways, always concerned about matching your verb with your subject. The equation x minus x naught quantity squared divided by a squared plus y minus y naught quantity squared divided by b squared is equal to 1 is called an ellipse. And they're saying that a is bigger than b in this case. And then you have ellipse with foci, that's the focus points. And then there's a C thing that's introduced with the foci. And then the center is going to be x naught, y naught, and the vertices are located offset. So in this case, where a, that's the denominator under the x squared, where a is bigger than b, then your ellipse is going to look like, and I'm just going to put it as if it was the axis, but instead of calling this 0, 0, I'm going to call it x naught, y naught. And our very first example will be 0, 0, of course, but it doesn't have to be 0, 0. It could be moved around. So your foci are these points over here. And then in the definition, they're saying that the distances, the sum of those distances from the foci to some random point is going to be the same all the way around. And you might have seen, you can Google YouTube for the ellipse, and you'll see somebody drawing it out with 2 nails and a string, and then they draw it out, and you get the shape of the ellipse. This is, it has not 1 vertex, but 2 vertices. And then c, by the way, is the square root of x squared plus, or a squared plus b squared. This distance here from x naught to the edge is going to be a. The distance here from the center point to this other edge is b. Sometimes it's called the major axis and the semi-major. Maybe it's minor. I don't know. I forgot. Sometimes they have names for these axes. Okay. When x naught and y naught is equal to 0, it's an easy thing to do. But when x naught and y naught are not equal to 0, you might have to do some completing the squares. And so what I want to do next time is to finish up the conic sections. And I'm going to want us to be able to distinguish between the different conic section shapes. So one of your quizzes this week, probably on Thursday, well, most likely going to be on Thursday, will be, I will show an equation, and then you'll let me know what kind of conic section shape it is. All right. See you guys tomorrow.